Hello, in this video we're going to look at working out the moment of inertia of a uniform rod. So this is a stick. So we've got our stick, which is just long, thin. It's going to be uniform, more uniform than my drawing, and it's going to be rotating sort of this way, sort of end to end rather than spinning round. So it's yeah, that's the direction of rotation. We'll put the axis of rotation in later on. But how are we going to actually go about getting the moment of inertia of this? So let's go back to our definition of what the moment of inertia is. So this is the sum. We have to sum up all of the bits. So this is n bits we're going to split the rod into, of the mass of that bit and the distance squared from the axis of rotation. So this is the formula that we're going to be using. So let's try and quantify all of these bits in. So say the mass of the whole rod is m. That's the mass, capital M is the mass of the whole rod. So the whole lot of it. So the lowercase m is going to be the mass of a little bit of it. And we can say that the length of the rod is capital R. So now we can chop this rod up into little bits. So let's take a little bit of it. So say this is our small amount of the uniform rod that we've got there. Now that little bit there, we're saying has got a mass of lowercase m, and it's going to be at this distance r from wherever we put the axis of rotation. And we can also say that the length of it is dr. It's just a little bit of r. It's a little bit of the length of the rod. So now we can put all of these bits together and say, okay, well, the mass of this little bit, so mi, just that little bit, if we chop this rod up into I pieces, we can say this is mi. So it's got to be the mass of the whole rod multiplied by dr over r. So that's the fraction of the length. So m is the mass of the whole thing, and dr divided by r is the fraction of the length that we're looking at. So that's our mi. And now, I mean, the little r is the thing that we're going to be integrating over. So we can put all of this into our formula here for what the moment of inertia is. So we've got m dr over r, that's our mass. Then we've got r squared, and we're going to be integrating this over some pair of limits on our integral, depending on where we put the axis of rotation. So two common places for putting the axis of rotation, we might put it in the middle. If we're putting it in the middle, then we're going to be integrating from minus r over 2 up to r over 2, because we got half the length on either side. Or we might integrate, we might have the axis of rotation at one end, in which case we're going to be integrating from 0 to r. So it depends where we're going to put the axis of rotation as to what moment of inertia we're going to get as a final result. Because remember, the moment of inertia depends upon the distribution of the mass, and the distribution of the mass depends on where we're putting the axis of rotation. If we put the axis of rotation at one end of the rod, then we've got, this bit here is much further away from the axis of rotation than we ever get when we put the axis of rotation in the center of the rod. So the moment of inertia is going to be changing depending on where the axis of rotation is. So that's just going to vary our limit. So let's do this twice then. So let's integrate once for, so say, let's go with the middle of the rod first. So this is for middle of rod rotation. So we've got I is going to be the integral from minus r over 2 to plus r over 2. And notice these are capital R's because it's talking about the extent of the whole rod. This is the actual physical dimensions of the rod, whereas these little r's that we've got that we're actually integrating over is moving our little piece, this little bit of the rod that we're dividing up. It's just moving through every little bit of that along the length of the rod. So yeah, be sure to not mix up your capital R's. Capital R is a constant. The lowercase r is a thing that's varying over the integral. And m is also a constant, so we can put the two capitals on the outside. They're not affecting our integral at all. So all we're actually integrating here is r squared dr. So that's fine because we know how to do that. So we're going to have m over r, and then we've got r, little r, that should be little r cubed over 3, and that's going from minus r over 2 to r over 2. So we're going to have an r cubed over 24 plus another r cubed over 24, so that's r cubed over 12. So we've got m over r times capital R cubed over 12, leaving our final result being mr squared over 12. So that's if we've rotated about the middle of the rod. So if we were going to rotate about the end of the rod, we're doing exactly the same thing, except we're changing the limits. So we can jump straight in at this point here after we've done the integration and say, okay, well, we've still got this. We've got r cubed over 3, but now we're going between the limits of 0 and r, which means, well, the 0 is just going to disappear. So we will have m over r times r cubed over 3, which is going to leave us with mr squared over 3. So that's quite a big difference. It's 4 times bigger, the moment of inertia, when we're spinning it about one end rather than about the middle. This is the standard approach for when we're looking at these two-dimensional objects. We're only changing in one dimension here. We're only integrating over the length of the rod. So these ones are easier to do. The rod is usually the one that people start with, and then we can go on to things. We can have a ring, and then we can turn that into a disc. These are still, we're just moving in this. It's a two-dimensional object that we've got here. So the one-dimensional things like the rod, and then the two-dimensional things like rings and discs, they're the easier ones to do. And then we'll start moving on to looking at the three-dimensional objects, shells and spheres and things like that. But yeah, this is always the easiest one to start with, and we can work out wherever we put the axis of rotation. We just change the limits and we get a new moment of inertia. It's fairly straightforward. So yeah, nice start on how to work these things out.